well, we'll see about that. First, a couple of updates about the schedule for this and next week. Today I'll lecture first, and then there is room to practice. On Friday I will lecture as well. It's not completely sure yet where, because the auditorium is taken because there are open data, so it certainly won't be here. I'm still waiting to hear where it is, but I'll let you know through a announcement. I'll add some exam information there as well. Next week there will be the professional skills session. I think that will be in auditorium 3, so if you don't hear anything else, then it will be in auditorium 3. We need to split the group in two. It'll take 2 hours on Wednesday, hours 5 and 6 for half of it, and on Friday, hours 3 and 4 for the other half. I'll divide you at random, and that's the part where you need to show up. On Wednesday, hours 7 and 8, I'll do some more exam preparation. It would have been a bit more convenient, I think, for everybody to have these two interchanged. Wednesdays 5, 6 and 7 and 8, but that didn't work out for the schedules of the teachers doing the professional skills part. So this is how it's going to be. Any questions about this stuff, professional skills, the schedule, and so on? Yeah?
What if you have to be notified about the professional skills sessions?
What do you mean?
Because I got a message about the professional skills sessions. So
What kind of messages are you looking for? You want me to wait? No, I think that might be related to the fact that the exact dates weren't yet known until very recently. So in all likelihood, I think you'll get an email from stuff in there, but you have to show up for one of the two meetings, and I'll let you know. If nothing else about this, then one final note. There was a quiz that you had to complete, or actually had to redo, before January 1st, and that's passed now. I got a couple of questions. I thought about it all the time, but I, in the end, forgot. So what I did was I extended it until this Friday. If you haven't done it yet, I gave you a small penalty for forgetting, and we now score 32 out of 36 for 33. And if you haven't completed this by Friday, I'll come up with an extra assignment that you have to do to complete the course. So do make sure that you do this. Get it over with. Okay, here we go. All the stuff in gray, we did that already. We went from, okay, Stata was that, and X and Y, and hypothesis testing, and t-tests, and chi-squared, and multiple regression a couple times, and now at the end, sample size we did as well. Now we end up with analysis of variance, and there are a couple of different flavors, all slightly dissimilar to each other. Analysis of variance or ANOVA, analysis of covariance or ANCOVA, and factorial analysis of variance. Yeah. That will depend a little bit on the time and on whether or not I can get a lecture hall on fire. So these we're going to go through, and well, just to make this absolutely sure, we're sort of going haphazardly through what a general setup of a paper should be. Normally you start here, you think about what your study design should be, and then you think about how large your sample should be, so that's normally the first thing that you do. We did it somewhere halfway. Then you measure your X's and your Y's as good as you can, and then in the end, when you get your data, you need to do something with it. For instance, these scale scores that I still have to talk about, or the factor analysis. Factor analysis is something for the next course, so we won't do that here for sure. But both of these have in common that it is more of a measurement than it is really analyzing the data. So you want to get better variables here than you have, and here in the end you have all your measured variables, and then you try to make sense of what you have. And there we have our chi-square tests, our t-tests, our multiple regression, and analysis of variance in different kinds of flavors. So this is stuff that you have way at the end. Okay, let me give away the main takeaway message, and that is this. There are actually two. First, all these OVA flavors are basically special special cases of multiple regression. So in principle, all of these you could do with multiple regression if you would know how. So the fact that we have separate commands here is part historical and part convenience. So we will see in a minute exactly how these are the same, and also why these different commands are actually there. But you could argue, why don't we just get rid of one of the two if they're the same anyhow? And the reason for having two is actually right there. Analysis of variance is something that came up, let's say, based on experimental psychology. You do an experiment and then you are trying to figure out, has the experiment worked? I'll give you a couple of examples in a minute. Whereas the other stuff, the multiple regression stuff, comes from typical survey data. You have a large data set, where large means lots and lots of variables to work with. You try to come up with a proper representation of your data. That this is actually completely the same. So analysis of variance is one specific case of multiple regression that is mentioned here and there in the book, but not as well obvious as it should be, I think. But we'll go through it and you'll easily see it. These are the commands that you'll encounter. One is ANOVA, obviously. Then one way and PW mean and PW compare are basically all further rephrasings of ANOVA. So that is again ANOVA but with a twist. There's a really weird reason why we have all these different kinds of commands. It would have been just as convenient to simply have ANOVA with lots of different options, but that's not how it is. Then a command that's called Closeness. That's typically what we end up doing if none of the assumptions are met. Then you need something where the assumptions do not bother you so much, and that's that other command. And all that stuff you can find in chapter 9. And there's a reading guide online, or almost online, where you'll see exactly where in chapter 9 you can find these different kind of things. Okay, so let me go through what the different commands will look like in a minute. So we'll see all these in more detail, but here you see, for an example, where our y, once again, is an interval scale variable. It's the only thing that we look at here. Our x1 is categorical, and our x2 here in this example is interval. First you see here, ANOVA y x1. This is something that looks like regression, but really isn't. In regression, this will be wrong, because if x1 is categorical, you need to create separate dummies, and include, if you have 5 dummies, 4 of them, or write I dot in front of it. Here, if you do not tell Stata otherwise, Stata will assume that this is a categorical variable, and will deal with it appropriately. So, in that sense, it's convenient, because you don't have to create any dummies, Stata will do it. Then there is an extra option here that's called Bonferroni. That's related to if I want to compare lots and lots of different categories. Let's say my x1 has 10 different categories. I want to compare 1 with 2 and 1 with 3 and 2 with 6 and 2 with 7 and so on. Then you need to somehow deal with that. More about that in a minute. There's an extra option there, and it would have been nice if that extra option could have been added there, but you can't. Don't really know why, but that's how it is. Then if you want to add an interval scale variable, if you just type x2 behind ANOVA, that's not going to work, because by default, Stata will assume that it's categorical, and in this case it's not. So what you have to type in front of it is a C dot, where C stands for covariant. Again, would have perhaps been nice if you could have typed I dot for I interval scales, but I was already taken, of course. That will create separate dummies. So here it is C dot for covariate. And if you do not want to make an interaction effect yourself, you can tell Stata to do it with that hashtag in between. So what this does is create, besides x1, we had it already in C dot x2, we had it already as well, the product of these two. And if you want to summarize that even more, you can do like this. 2 variables, x1 here, and C dot x2 over there, and 2 hashtags in between. That will be interpreted as, what you apparently want is x1 itself, C times x2 itself, and the cross product of the two. So all shorthand versions of these same things. All of that you can do with regression as well, no problem. You can simply create the separate dummies for x1. You can simply include x2 as an interval scale variable, and create by hand the product of the 2 variables, and include that. All perfectly fine, you get exactly the same results. Yeah?
Is that including interaction effect? Does it also include the covariate? Or is it just the interaction?
Here, with the single hashtag, that's just the interaction effect, and that's fine here because I have here the variables themselves already in it. Here, this is exactly the same as there, so you get both the main effect and the interaction. Okay, so let's see. Here, the equivalent commands on the right side for the ones that we had on the left. So y x1, well, that will be regression y and idle x1. X1 is categorical, same thing. That Bonferroni thing that you see there, well, that we cannot do with regression. Would have been nice to have it perhaps, but it's not an option there. And the analysis of variance with the separate interval scale variable over there would be equivalent to doing this. I dot for the x1 and x2 separately as an interval scale variable. So mainly what it looks like now, and perhaps this is the case, what it does is mess your mind up, because all of these are, you know, slightly different in terms of what you need to write, but in these cases it's exactly the same in what you get. So we'll go through exactly what the differences, the uses are for the different ways of writing this down. Okay, so there we go. Analysis of variance, and the standard example of, let's say, a psychologist's kind of experiment is, let's take that Milgram experiment again. This is where you have somebody there, this is the subject. You tell the subject there's somebody else in the other room. That person will have to answer quiz questions. If the quiz question is answered incorrectly, you need to administer some current to the other person. And the more they have wrong, the higher the current is supposed to be, or higher the voltage, as you say, is supposed to be. And you see here on the machine that it's going up and up and up and up. And we're trying to figure out, well, first of all, whether or not people do this, and we know they do, and under what conditions they do this more than otherwise. The example here would be, well, let's look at first the dependent variable, that is voltage. How far on the machine are you willing to go? And the treatments that we have is condition one, there's nobody there, just you. And the second condition is there's somebody there, but wearing jeans. And the third condition is there is a person there wearing a lab coat. And we're trying to figure out, does that make a difference? If there's nobody there, then at some point you think, okay, I'm going to stop this, I'm not going to continue giving extra shocks. The person in jeans who is there standing will perhaps make you a bit more reluctant to actually stop. And a sort of official person in a white lab coat will make you more reluctant to stop, might be the argument. If you have this is a categorical variable, that is a interval scale variable, that is our dependent one. And what we do is we create separate dummies, one for this one for this one for that one, and we include two of the three dummies in the equation, so we have voltage equal to V0 plus V1 times the G's condition plus V2 times the lab coat condition. You estimate the model, and in the end you get something like this, an estimated V0, that is exactly the mean of the control condition. So if people are willing to go on average up to, let's say, 112 volts, then that is the mean for that condition. V0 plus V1, that is what you get for the person in jeans, and V0 plus V2, that's what you get for a person in the lab coat. Now do note that these are the only ones that you're going to get. So your prediction model here is consisting of basically three numbers, one for each condition. You give a mean for each of the three conditions, and that's it. So if you look at this in terms of prediction, this is not going to be very good. Your prediction model consists of three numbers, and it's the same number for each and every condition. So that's not going to work very well. But it does allow you to check all kinds of different hypotheses here. Of the kind, well, for instance, the first one is the condition where you have no person in the room. Is that the same as the condition where you have a person in jeans? And that test is actually, the test is B1 equal to 0. Second one here, no person in the room versus person with a lab coat in the room. Is there a difference there? Well, that's exactly testing that B2. Does it make a difference if there's a person there, if the person is wearing jeans or a lab coat? That is testing, is B1 equal to B2? And doesn't it matter at all, perhaps? That would be testing, is B0 equal to B1 equal to B2 equal to 0? I should perhaps add. And you could test a couple more things that are, let's say, less easy to rationalize, but testing is the coefficient of the jeans condition half as large as the condition, as the coefficient for the lab condition? That's also something you would be able to test. In any case, all these things are simply comparisons between conditions, and that's it. And a typical psychologist's experiment is of that kind. You know, the control condition and we do the light on, and we compare, has it made a difference? We have a control condition, we give you an IQ test, and you have a control condition, we give you an IQ test, and before that we give you 10 cups of coffee. And we check, is there a difference? And the only check that we do is on the averages in the conditions. Okay, so, yeah, that's it. And that's in a way a bit weird, because first of all, this is nothing new. We did this in multiple regression. Usually we also had interval variables there, because we started out with scatter plots and stuff like that. So then the predictor variable usually was interval, or at least there was an interval variable in there. But if you have just one categorical variable, that will work as well. So this we can already do. For instance, if X is categorical with 2 categories, then this is a t-test. And even if you would run with multiple regression, this would work. And that immediately shows what the equivalence of all these ANOVA variants is in terms of the predictor variables that you have. So this is one factor, this example, experimental clothing, and the factor has 3 conditions. If that's all there is, okay, this is called ANOVA. If you have a covariate in there, so something that is measured, a measured interval variable, for instance, how old the subject is, if you add that as well, it's called analysis of covariance, where the C comes from the fact that this thing is usually called a covariate in analysis of variance. And if you simply add another factor, for instance, there is a sticker with some text on the machine, again 3 conditions. First, there is no text there, so that's the control. Or the one is follow the instructions of authorized personnel, or danger can cause lethal injury. Then again, you have 3 conditions here. Together with the first 3, you have 9 different combinations, and you can compare these 9 different means with each other. And then it's called a factorial, well, ANCOVA if you also have the covariate in there, factorial ANOVA if you do not have the covariate in there. But, you know, all this is just multiple regression. We have a bunch of predictor variables, and depending on what we have, we want to compare the different conditions. As you already have noticed, there is a bit of terminology that is more or less standard here. Something that's called an interval scaled variable is here called a covariate. And something that we used to call a categorical predictor is in this neck of the woods usually called a factor. And it really means exactly the same thing. Just so you know that if you read in a paper somewhere analysis of variance, you'll typically read factors and covariates. Okay, so let's take an example here, trying to emphasize why all this is actually there. And I hope that you can already see a little bit where the argument is going. If you have survey data, then you typically have lots and lots of measurements, and you have these lots and lots of measurements. We did that 7 or 8 weeks ago, because in non-experimental research, you have to take into account all predictor variables that correlate with y, the thing that you want to predict, and your other predictors. So you keep thinking about, okay, what other variables might predict what I'm interested in here? And in the end, you come up with a long list, and then you see my survey is going to get too long. Okay, let's take only the most important ones, and then you have a big survey, and you get a data set with lots and lots of variables in it. And then you try to see what's going on. There you get your, well, where are my outliers, my transformations, my various inflation factors, and all that stuff that we did there. We have it because we have so many variables, and we need to take into account that we model the data as, let's say, as closely as possible. Here, all this is experimental data, where, well, the researcher creates something, some condition of interest. For instance, this here is Jan11, a couple of years ago, I think, who did some research on this robot. The robot is meant to, well, for the beginning, I think, make you more aware of the fact that you can turn down the temperature of your washing machine. So it does something, you put it on your washing machine, it's connected to it, and if you put your towels on 95 degrees, it will suggest to you, well, perhaps 65 is good enough. So there are a couple of conditions here. We have people with a washing machine without the robot, we have people with a washing machine with a robot, and the robot says A, and another condition perhaps where the robot says something else. For instance, A condition could be the robot says something in a nice way, So it says, great, you only put the washing machine on 30 degrees, which is excellent. Or the other condition would be, if you put it on 95, that it says something nice. Okay, don't do this. You're ruining the environment, and tune it down a notch. And then we check if it makes a difference. Okay, but all the interesting stuff here is not so much about modeling the data, because there is not that much data. And the data that you have is categorical. You have groups to compare. That's all there is. Okay, so this is one example from the survey area that we did, that I did together with Gerrit. Your dependent variable is how well a firm is doing, and we have data from the Fortune 500 who has board members who are also in the board of other Fortune 500 companies. And the idea would be, if your board members are tightly knit in the network and know all the other parties there very well, that is in general good for your business. Well, check that, but there's nothing experimental about it. It's just measured data, nothing else. So we need to have lots and lots of predictor variables that all say something about how a firm is doing. Then you get a long list of companies, 500 in the Fortune 500, and a long list of predictor variables. All predictor variables say something about how a firm is doing, and you try to make sense out of that. And you get all the transformations and the outliers and so on. This is a typical test that we might be able to do in the lab. This is Untitled Hans. Here you see sort of a big picture there of somebody wearing a VR setup here. No, there's not another one. You are in principle here in an empty room. You're standing there, and what you see is a pit. The pit stretches down there on what is now green here, and you could have a couple of conditions. For instance, how deep is the virtual pit that you're looking in? So one would be 2 meters, or 6, or 15, or 50, looking down. And the other thing is, well, that thing over there, that's a piece of wood. And I'll show you in a minute why that would make a difference. If you forget about this piece of wood, here is wood as well. If you make sure that the wood is there and that it is a little bit above the actual ground, and if you wear the VR set and you're walking towards the virtual edge, so to speak, you feel that your toes are now no longer touching the floor, which makes the experience stronger, and it makes it more likely that you are fearful there. And you could have a couple of covariates included as well. How old are you? How often do you play video games? Or do you have fear of heights, or who knows what? And yeah, just to give you an idea, see, can we get this to work? So this pit is working stronger in the sense that, see, you have that extra piece of wood over there that you can walk onto, and you feel it with your feet as well. This one has a nice interface where you can actually drop a ball into the pit there. It's actually not so obvious how to measure here how fearful somebody is. One would be measure heart rate, because the more fearful you are, the higher your heart rate will be. Or sweat might be an idea. Simply asking afterwards, or even during, might be an idea. Okay, so we get it. Okay, so again, if this would be the variation that you have in there, then in the end, the only thing you want to compare to get an idea whether or not this matters or not isn't just a couple of categories. You have a mean for category 1, a mean for category 2, and you compare the, yeah.
Why did you say covariance gender? Because gender would then be a factor, right?
No, factor is not related to whether or not the variable itself is categorical. Actually, covariance is something that you can measure and not instill on the subject. Okay, so it's not that, okay, you come in and I make you male. You are male already, and I measure it by looking or by asking. So the point is not so much here that this is something that necessarily is interval scale, but the point is that this is not something that is determined by you. So, for instance, asking for, do you have any fear of heights? That would also be covariance, something that is measured. Okay, something on our own data, because we had this as well. I don't remember exactly, because this is from a previous year. We had something that is similar, at least. Here the question was, I have to check. There were two questions, in fact. The first question was, do you think that there are more or less than 200 countries in Africa? One third of you, or one third of these people got that question. The other third got the question, do you think there are more or less than 60 countries in Africa? And the final third got the question, do you think there are more or less than 20 countries in Africa? Okay, the true answer is about 54. And the idea we are checking here is not so much what you answer here, but whether or not if you are in this or that condition, if that influences what in the end you answer to the question, okay, what do you think? What is the number of countries in Africa? And the idea would be, if first I ask you, is it below or above 200, that your guess is going to be higher than if I start from, okay, is it below or above 20? This will suggest something, well, in all likelihood it won't be 254, whereas here perhaps there still might be an option. Okay, so let's see. Here we have the means in the data set here. Simply a table, the mean of these numbers, 37 for the 20 condition, 49 for the 60 condition, and 70 for the 200 condition. So certainly it looks like, well, not only it looks like, these numbers go up. The only thing that I need to check here is, are these significant differences, yes or no? So the manipulation in that sense has worked. And what I'm about to do is create dummy variables here through the tab command. I saw that 39 people are in this condition, 40 there, and 29 over there. And I now have variables in my data x20, x60, and x200 representing the separate categories. Okay, normally I, of course, have to double check, is there any weird stuff in my data, but at this point I forgot about that. Okay, now I run my multiple regression. Standard stuff, regress number of countries, that is the guess that I got, and my two dummy variables, 60 and 200, and 20 condition is left out. So what we see here is, well, this is borderline significant, but not. So apparently there is no difference between the 60 and the 20 condition. That's the interpretation of the first one. And here we see this one is highly significant. There is a difference, a statistically significant difference between the 200 and the 20 condition. And here what I added there is test 60 equals 200 equals 0. So this is testing, does it help at all that we add these separate dummies? And the answer is, oh yes, because this thing is indeed a significant difference. Nothing new, we did that before. These here deliver exactly the same thing, but in a slightly different way. You could argue here this is typical psychology stuff where you have an experiment and a bunch of conditions. So what we want here is an analysis of variance, where we have a number of countries in our thing that we want to predict, and that X countries, the categorical variable that I created the dummies from, as the one that is predicted. And now what I get is something that looks like this. So again, one of these tables where we have sums of squares and then r squared and stuff like that. And the only thing that I now get back is the 0.0001, and that is exactly that number over there. The test of, does it help at all to include these different categories? And again, the answer is, we reject here that it doesn't help. Suggestive of the fact that indeed, there are differences between the categories. The disadvantage of this is that you only see, there are differences between the categories here, but you do not see where. There you can simply see where the differences are, and here you don't get this. You can later on, but you do not see it immediately. Okay, let's see. Yeah, some other tests, of course, that we've seen before. I can test, for instance, if these two are actually the same, because I compared 20 with 60 already, 20 with 200 already, and not 60 with 200. And if I do that here, then you see, well, indeed, these are also different. We reject equality. So by hand, here it's relatively easy because we have only 3 categories, but I can do all the comparisons separately. Let's see. Then now our step up to, well, first of all, we saw that ANOVA command that will give you the crude estimate of whether or not the variable is helping at all. It did. I can do that in another way as well, through the command that's called one way, and then I get basically the same answer, slightly different output, but again, the F value of 10.55 and the highly significant score in the end. So this doesn't help us much yet, but that one-way command has a couple of options that are useful for us, and these are the ones that we're going to use. Let's see. Oh yeah, this I had. All the same. And now we see what is convenient about this. Here we have 3 of these different categories, but if we would have had, say, 15, a categorical variable, 15 different categories, we would like to know whether or not there are differences between all of these different categories. There is a way to do it, but the disadvantage is, if I want that, then I would have had, well, 1 with 2, 1 with 3, 1 with 4, which is a big bunch of tests, and that causes that if I run enough of these tests, what I will find is that I get significant differences simply by chance. There's a 5% alpha value, so 1 out of every 20 times I find something that is significant in my sample, but that is not significant in my population. So you have to somehow take into account that you test so often. And there is a way to take that into account, and that's called the Bonferroni correction. Bonferroni is counting, okay, how many of these comparisons are you actually making? And given that, I adapt the significance test to that number. In this case, it doesn't make that much of a difference because we have only 3, so we're not running so many tests, we're running only 3. But still, if you ask for this, first you get the same thing, so this output we saw already in the previous page, and then you get all this. Comparisons of all the different categories that you have, well, whole is here only 3, and you see one over there, the difference is 11.9, non-significant, that's between 20 and 60, between 20 and 200, the difference is 33.5, the difference is significant, and the difference between 60 and 200 is 21.6, and that difference is also significant. And what you will see is that if you check these numbers, these significance values, in this case, the actual answers, significant or not, do not change, but the values that you find here do change. So what can happen is that if you check without the Bonferroni correction, you find significant differences, but you don't find them anymore after Bonferroni has been let loose on your data, so to speak. Okay, so this is quite convenient, especially if you have categorical variables with lots of different categories in it. That Bonferroni is unfortunately only one way in which, okay, I had that before. One way in which you can do this. Oh, I had an exclamation mark. That must mean that I have a difference there, I think. Double check. Yeah, no, not really. Here you saw that this one was 0.08, it's between 20 and 60, so let's say almost statistically significant. And there you see, well, still not significant, but really not, so to speak. So if you include the Bonferroni testing, then you really see, okay, even though the 0.08, I would have been tempted to think almost, still it actually is not. And here you see something that makes matters in a way more complicated. There are different ways to do this. So in one way, you needed that because in ANOVA you couldn't add Bonferroni. So you need to type one way and then add Bonferroni. In that one-way command, there is another option. There's another guy who came up with an idea to control these things called Scheffer or Scheffer, I'm not sure. And that's also an option there. But there are actually more ways to do it, all there. And with a command that's called pwmean, you can do all those. Which is sort of weird because in principle, all these, ANOVA, one-way, and pwmean do the same thing. It would be nice to have one command with all these different options in there, but we don't have it. So if for some reason you think that here it would be better to control with the two-key way, for instance, because the reviewer of a journal asks for it, then there's only one way to do it. Find that pwmean command first and do it then. Okay, I won't go into the details of all these differences that are relatively slight. You need to know the Bonferroni difference and how to get it from this data. And what you also need to know is that there are different ways besides the Bonferroni way to do it. Okay, just to show you that that matters are even worse than they seem, where that one-way command was simply putting one way where the ANOVA word was, easy. Here it's actually slightly different. For the PWE, you need number of countries and then a comma over X countries, ask for Bonferroni and compare, and then ask for effect. Okay, so not very convenient, but you know, it's possible. Okay, brief note about all the statistics packages that you see here and all the ones that you don't see here. For one reason or another, all these statistical packages have separate modules for what they call analysis of variance and for standard regression. So you might think there is a statistics package out there that simply combines it all into one, which would have been a good idea, I think, but as far as I know, that's not true. And this means, for instance, that if you run, let's say, an experiment where you have 3 or so covariates, you can do this with the ANOVA command. At some point you might think, well, actually it's not such a bad idea to look at where the outliers are in my data set. Yeah, it's indeed a good idea, but the df beta command that we saw before that will give you where the outliers are is only possible after regress. So you have to run the regression that is analogous to the analysis of variance that you ran before, then run the df beta command, find the outliers if they are there, take care of these outliers, and then perhaps go back to that analysis of variance. And it's the other way around as well. If you want to control for the Bonferroni thing, it would have been nice to do that also in multiple regression, but you can't. So you have to be able to mix between the two and use whatever works best for the given circumstance. Okay, assumptions. Well, we had t-test, interval y and 2 groups, and this is just an extension of that. You have interval y and more than 2 groups. So the only thing that makes a difference here is that you have more groups, but the assumptions do not change at all. So we have, of course, also an assumption, you would argue that y is interval and x is categorical, otherwise we're not doing this at all. We need that y is normally distributed for each category. We saw that for the t-test as well. The only difference is we now have more categories. And we have, if this is violated, our standard repertoire of trying to transform y in such a way that it becomes normal, stuff like that, all the same. And the only difference is that in the end, if that doesn't work, we have something that is called rank sum for the t-test, and we have something here as well that's called K-Wallace for Kruskal and Wallace, which is the parametric version of the analysis of variance, just like rank sum was the non-parametric version of the t-test. I think I have an example of it. Oh yeah, so if I do the testing actually here, so now we do it, the only thing that differs is we need a little bit more work. We now have 3 categories. Swilk will test for normality. Okay, violated. So apparently what we did before here, actually we shouldn't have done this at all because that analysis of variance assumption is not met at all. At this point I didn't try any transformations, just to show you what would happen if in the end you find no transformations of my y variable don't help. Then you type this, the Kruskal-Wallace command that uses, as we saw before, it's a long time ago, but if you look it back again, it uses the ranks, I have that here I think, yeah, of the different variables, and what you then get again is a test of this kind. We have here our 3 groups. We look at the rank sum for the different groups, and we compare that with the ranks that we would expect if there are no differences between the groups. We see here that inequality is violated. So this is suggesting, yes, there is a difference between the groups. It doesn't tell you between which ones, just that there is one. If you want to know if there are differences between specific groups, then the only way that I know of to do it would be to extend the command with an if statement. For instance here, if I want to compare this one, that will allow me to do the separate comparison over there, and that'll work. So if I need to do this for a categorical variable with 15 categories, this is a nuisance, and there is no faster way. Again, you might hope that you have one of these one-way commands or a Bonferroni correction or what have you, but it's not standard, and you have to simply do it by hand. All the same as the standard stuff. All right, so the bad news is you get now different kinds of ways to do this. You can test between categories with and without the Bonferroni correction. That can make a difference. You can also test looking for outliers, yes or no. You can test after you have transformed your variable to be normal, and all these things might be slightly different. So if you're lucky, you try a couple and it doesn't make a difference. You get the same answer irrespective of what exactly it is that you do. Great. The tough part comes when you find that, okay, if I use that Bonferroni correction, I find no significant effect, and if I do something else, I do find a significant effect. Now you simply need to think very, very hard which of the methods that you try is most appropriate in that particular case. No general rules for that. So it's not so much only, this is also a nice tip for the exam, don't write as an answer to any kind of question, you know, just the code for ANOVA and then the output, and then not, okay, what do we see here, what is the conclusion? The conclusion is not P equals 0.03, the conclusion is there is no difference, or that hypothesis is rejected, or there is no evidence in the data for this or that. You need something of an explanation there. However, yeah, even though it is actually, it's sort of storytelling what is in the data much more than just running the numbers, that doesn't mean that anything goes. It has to make sense what you say, of course, so you can't just say anything. But nevertheless, it is a story about what's going on in the data. One small thing that I want to get rid of before we go to the break, that is some nasty bits that I, at first I thought I would just sweep it under the rug and nobody will notice. But instead of sweeping it under the rug, let's just sweep it in plain sight. If you pay close attention, you might have noticed that there are a couple things here that should actually be the same. We have analysis of variance, where our predictor has two categories. Okay, that's the same as a multiple regression with one predictor with two categories. And it's also the same as the t-test with a group where you're comparing two categories. All of these should deliver the same. Now what we did in the t-test was we said, well, this is the standard command, t-test y by x, but we don't want to do that by default. By default, we'll do something that is not standard in this data. We don't bother testing that the variance in these different groups should be the same as well, because it has been shown by now that this is actually a good idea, whatever the variances are in these different groups. Well, this we do for t-test. If you do this through analysis of variance, there is no option to say unequal. So it is a bit weird that the default that we choose for the t-test is actually a different one that we choose for analysis of variance, even though in principle the two analyses are the same. Okay, we're not going to be bothered too much by this, so it's just that you know that there is a slight issue there. I'll start the second hour in a minute with an example where the example is based on experimental research, where the idea is to take an hour to get close with a complete string. The example that I'm about to show is there for a couple of reasons. First, this is your typical psychologist example, where you see that in the actual paper that goes with it, analysis of variance plays a quite prominent role there. That's one reason. The other one is that this is a very good example of how the actual paper is way different from what people in popular media made from it. So the whole experiment itself, because it was an experiment, is about creating closeness between, in principle, I think, complete strangers. And in the end, the experiment worked in the sense that closeness had increased between complete strangers. And then this is what you got in the popular press in the end. The idea was here, well, we are creating love in the lab, 36 questions that spark intimacy. And I checked the, let's say, the urban myth that followed this, because one of the stories that goes with it, I'm not really sure if that was actually true, but it is that from the people that participated here, in the end, two of these more or less random strangers ended up being married. So that caused that, well, these are the 36 questions that can connect you to, let's say, in principle, a totally random stranger, then this is, well, quite interesting work. So let's see what actually happened, and then we'll see to what extent this is actually working. The paper itself was indeed called Creating Love in the Lab, and this is what it said. It said a lot, but here you see the results of only study one. This is study one comparing closeness, and there we got a composite closeness score. We'll see what that was in a minute. Of 4.06 for the closeness condition, and a score of 3.25, so a little bit less on the small talk condition. And that difference, again, says, corresponds to an effect size of 0.88 standard deviations. That's something that we could remember from when we did multiple regression here. There was an option there that was called beta. You type beta behind the multiple regression, you get all your coefficients in terms of standardized scores. Your predictors are standardized, your y is standardized, and you look at the actual effect size. Then we heard that Cohen, also mentioned here, suggested that anything, let's say, above 0.5 or 0.6 is actually a large effect. So an effect here of 0.88 is really large. So apparently the manipulation here is working quite well in that sense. Let's see. This is what we did. Analysis of variance here. A 2 by 2 by 4. And 2 is half. 2 is cross-sex, so it's all women. And 4 is the attachment style pairing. With the pair as the unit of the analysis. Now let's see what all that was. First, we're trying to measure closeness here. That already is not so easy. You're looking at two random people and you need to ask, okay, how close are you? It's not that obvious, and there have been quite a few scales, some of them quite extensive, where you have to answer 35 questions or so, and then we determine how close you are. This was actually one of the questions that was being used there. There were only 3. One question was, okay, this is you and the other, and pick any of these 6 that feels most representative of how you feel towards the other person. And the closer you choose, well, the closer you apparently are. That's the idea. You can put this on this one on a 6-point score. In fact, I think the one in the journal was actually a 7-point score. But anyhow, there were 2 other questions there, and that's the score you get. So you can have at worst a 3, and if you're really, really close, you had a 21. So that's an interval scaled Y. Then you have to realize that, well, there are a couple of conditions here. We had this one there, small talk, first play, getting close, same sex for different sex and attachment style. What was that? They took random pairs of people and let them talk. This was a psychology course, so there were more women than there were men.
I think something is being played or put
Yeah, what I could do when we little plug somewhere. I have nothing what I can do about it, I think. So we're trying to make pairs, 2 kinds of pairs, women pairs. We had that because there were more women than males, and boy-girl pairs as well. So that's one of the conditions here. 2 women versus boy and girl. That's a categorical variable, 2 categories. Then the other one was, well, they measured attachment style, and they created different kinds of couples based on attachment style. If I remember correctly, if you are, I think, avoidant, then you were typically matched with somebody else who also was avoidant, so you get matched in the end with somebody who is similar to you in terms of attachment style, something like that. There are 4 different styles, so you can have that. important. They all had to go through a set of 36 questions with each other. One set of 36 was just small talk about the weather and, it's just people are talking, that's it. The idea would be if you talk, that will help, and then you get closer. The other one is first trying something relatively innocent. Okay, if you want to be somebody really famous, who is it that you would like to be, and why is that? So that's still not very close in a way. Getting closer to, what do you like to do on a day where you in the end find out that you are really happy, and why did that make you so happy? And then you take turns, because it's not so good if you open up and then the other one doesn't open up back. So we want to have a bit of symmetry there, otherwise it's not going to work. And then in the end, after an hour or so, you have gone through almost 36 of these questions, or almost all of these 36 questions, and in the end, we measure again, did it work or did it not work? And if people say, I'm closer, then it did work. The main thing to get from this is, well, this is roughly the data. These numbers I just made up. But I want to show here that there are only 16 numbers in principle to work with and to compare. That's not nice, huh? Any idea where this is coming from? Besides from, now they're quiet, great guys, but the other stuff is coming from somewhere else. It is? How long later? I can try to go without. Have to speak up a little. Hmm? Really? Wow. Let's see. Okay. They're gone? Better? Not sure why that helped, but it did. Great. Okay, so I'll only hear myself. This is better. Here, a lot in the popular press about it. In the end, what we have only is 16 numbers to compare. We have 2 by 2 tables for small talk versus very close talk. Same sex, but it's different sex couples. And we have 4 different kinds of attachment styles that were paired. So even though there were quite a few people who have participated here, in the end, the only difference is that you're trying to figure out here are these differences, for instance, small talk versus very close talk, 3.5 versus 4 or so. And we're trying to figure out if that is a significant difference. And that depends also on how many people that we have, but in principle, these are the only comparisons that we're trying to work with. And that's typical for many of these kind of things, where you have something that you did in the lab. You gave these 36 questions for a couple to work with, and we compare it with people who haven't done this. And let's see, that in general you'll typically find in all these papers by psychologists where an experiment is being run. You have analysis of variables because this is what they are used to. You do not have a lot of variables because the variables of interest are typically the ones, the experiment, control condition, and something where you manipulate, perhaps something where you manipulate in slightly other ways, and that's it. And a handful of perhaps covariates that you have measured, but very often you do not measure that many covariates at all. In the end, usually the statistics is way easier, simply because the data set is way smaller. This you cannot read, but if you're interested or are looking for someone or who knows what, then you could try this 36 questions. You have them over here. You should make sure that you take turns. And if you have somebody already and you don't want to hook up with somebody who is trying to play this on you, then you also know which of the 36 questions you should avoid. They are kind of interesting. I'll put the slides online, so no reason to take notes. Then, a couple of small extensions in this that are not much different from what we had before, but we nevertheless have to cover them. Adding a covariate here. And covariate is, in our example, an interval variable x, but in principle all of this works the same if it would have been a covariate, a categorical one. First of all, we saw before in the ANOVA, we had ANOVA one way, PW mean, and there was still another one. It would be nice, given that they all do the same thing, that they would all allow adding a covariate, but they don't. Only ANOVA allows a covariate here, and you type it there. I think I have that. Yeah. So we add here the C dot for covariate high school grade after it. So here we have the analysis of variance on that guess on the number of countries in Africa once again. I add high school grade to it. This is the table that I get. I get an estimate there. A significance level way above 0.05, so apparently high school grade doesn't matter so much. And if I type regress right after, regress with nothing behind it, right after I did an analysis of variance, I get the actual regression that was being estimated. So the way this is being used to create that. So here you see the underlying thing there, and for instance, you'll see that 0.744 is exactly the same one that you see over there. And this one, the 0.0001, that is the number that you would get if you would type test this coefficient equal to that coefficient equal to 0. So they really are equivalent. Interactions is also relatively easy. A little bit decreased. They were easy means you don't have to create it yourself. The hashtag will create the interactions for you. That would be a bit nasty if you would have to type it by hand, because then you would have to create interactions with each and every separate dummy you created from your categorical variable, like this. Stable will do it itself. Yeah.
Was it the whole point of doing an experiment that you can get rid of all these covariances?
Yes, that is certainly true. So the argument would be, okay, I don't want any covariate in there, and I do not need any covariate in there, because what will happen is, if I have random allocation in an experiment, then whatever the other covariate is, will be randomly allocated and not correlated with my experimental conditions, and I need not worry about the experimental variable itself. Now that is certainly true, but there could be a couple of things why you would nevertheless want to covariate. First, if you are interested in the effect of the covariate itself. So now we're assuming in the argument that I just gave that the only thing I'm interested in is the experimental manipulation. But if I also want to know, does it make a difference if you're male or female or young or old, who knows what, then I can see it. And the other thing is the random allocation, in principle, should take care of the fact that there is no correlation between the two. But if it's something that I can easily measure, then I can also simply take the variable and include it, because there need not be an exactly zero correlation there. There might be a bit of correlation if I can. And then if I have it, then why not just include it? But don't forget the C dot over there, otherwise it doesn't work. I mean, no, it does work, but you get something else. If you don't put the C dot there, then Stata will assume that high school grade is a categorical variable, and then you get separate dummies for each and every value of your categorical variable. Not what you want here. Again, you type regress after an ANOVA, you get the regression table that goes with it. In fact, what you really want to do is regression, it might be easier to type the ANOVA way for the command, and then afterwards type regress. You get the actual regression that goes with it. This I don't want to do. Now, analysis of covariance assumptions. This is typically something where you see lots of different statistics groups saying different kinds of things. So this is what I suggest here. Analysis of covariance. So it's, on the one hand, you could argue, solution one here, that's easy. This is basically multiple regression, right? Because if we have a categorical predictor, so that's actually a set of dummies as a predictor, and an interval scale variable as a predictor, then this is called multiple regression. We know how to test our assumptions there, so it's simply treated as if it's slightly different, then this is possible too, as long as you don't have too many of these different kinds of covariates. So if you have something like this, where this is your y, and you have two dummy variables, d1 and 2 over there, and an interval scale covariate over there, and now I want to test my assumptions. Now normally what I would do is for each and every category, if I wouldn't have the covariate, check if my variable is normally distributed in each and every one of these categories. Well, here this is not possible so easily because this one is sort of bothering me. So what I can do is I look at this, I estimate this model, I get a value back here for that D3, an estimated D3. I create a new variable there, y estimated. Oh, sorry, this one should go. This is not an estimated y, this is the actual y. So y minus that estimated B3 times the interval scale variable. So I get rid of that interval scale variable and put it on the other side, and I give me a new y. And now I have a new y and just these two categories over there. So now I can do my assumption testing just like I did in analysis of variance. Now I have here the control group and condition 1 and condition 2, so 3 groups in which I have to test if there is normality over there. And I can do it, but I have to do it on the new y variable over there. What you also need is, something that you do not see everywhere in all statistic groups, but if you test a model like that, you are basically assuming that this effect here of that covariate, of that interval scale variable, is the same in all of the groups, and that you can simply test by including the interaction effect of this one with these separate dumps. But I think, in fact, by far easier is memorize very well how to do this, treat this as multiple regression, and go through all the things that you have seen there. Okay, that is adding one or more covariates. You just add them. This gives you some extra nuisance in terms of the assumption checking, but other than that, it's just multiple regression, different ways to get the same thing. Then a two-way ANOVA, if you add one factor, or three-way if you add a third factor. So you have another experimental manipulation in there besides just having the one that you started with. So in the VR example, so you have the piece of wood that's there or that is not there, and you have the depth of the pit that you vary. Again, this is a categorical x, so you can simply add it here on our own data. So this is similar data to the one that we have, but now for previous year. I asked you these kind of things. Do you think it's sometimes okay too? And then a bunch of things that you could agree to or not. Smoking cigarettes, committing a crime, which could put you in jail, keep things you find in the street, and so on. We can create an alpha score out of this, and that will simply count how often you say yes to these kinds of questions. So if you score high there, then you think that quite a few of these are in fact okay. Now I had a couple of things in the data that perhaps I could use as an example of a categorical predictor, and I took this one. It's actually not really an experimental factor here because it was measured, but there was nothing else that I had in the data that was experimental, so I just went for this one. People make decisions in different ways. What's your decision style? Well, you choose between these. And yeah, I cheated a little bit because what I actually wanted to do is for each and every one choose to, or let's say designate you to the group where you say that you are, let's say, most alike. So if you have totally not me all the time except there, then I would say that you are one of these. That doesn't always work because sometimes people say, okay, all of these are totally not me, so there is no preference for either one, and then I simply have to choose one. Or you have two where you say, okay, I'm certainly not one of these, but these, yeah, both of these are totally me. So what I then did was simply at random choose one. And that gives me different kinds of decision styles in the data, where these are the styles that we have. You're either logical, avoidant, consultative, intuitive, or of the snap decision kinds. And you can see already by the labels here that it might be possible to be more than one of these. Just to make sure that you have this complete, this is what I did as a do file actually to make sure that we get data like this. If you want to replicate this on our own data, it's possible with these bits of code. And this created, well, two things. First, an interval variable that says what you score on the it's okay variable. Great. And now we have decision making that has 5 different factors here. Sorry, 5 different categories here of 1 factor. We leave out 1, and we see here, well, not so much. The only thing that is significant there is this one. So apparently, if you are in group 2, then you score higher there than if you are in group 1. Let's see, if you are avoided, then you score higher there than if you are logical, for whatever that's worth. And what you don't see from the actual regression, you see from the analysis of variance here. If you type it's okay here and then just decision making, not the I don't now, because Stata will assume that you have a factor there. You see that indeed there is a difference between all these, so it does make sense to include them as a predictor. Okay, but that was just one categorical variable. Here I have another one. I don't think it really makes sense to include it, but nevertheless I did, simply because I found it in the data and I had used it before. The operating system that you use for your laptop, most of you use Windows, some of you use OS X, and a handful use Linux. And here you see that we have 3 categories of those, and the only thing that you simply have to do is add as a predictor variable, and there's nothing that you need to do in terms of making separate dumps. It's just done automatically. Again, what you see here is, if you have that, then we have, for the decision-making variable, yes, it does make a difference. And for the laptop operating system, that doesn't make a difference, which is not so even close, by the way, but it's not so strange because I wouldn't know why this would make a difference at all. You can type regress, that will give you all the underlying stuff, and again, here you see, if you have categorical variables with lots of categories, it is convenient to know these ANOVA commands because they give you all this without you creating any kind of dummy whatsoever, which is quite nice. And interactions, and there you see once again that double hashtag. Has decision making as a main effect, laptop operating system as a main effect, and the interaction there too. You see the interaction there is taken together, not significant. And also what you see is if you now get the output, and this is always a source of concern, if you get output like this, where you get empty cells, where you don't really expect them, it's time to have a look at your data if this is actually right. So here, you see so many of these different values because, well, decision making has 5 categories. Laptop operating system has 3. So if I need to take the interactions of all of these, that's quite a few, and it might be that in these 15 groups that I have, that not in all groups I have data points. If there are no data points for laptop operating system is Linux, and decision-making style is avoidant, yeah, then there is nothing that I can estimate in there, and then I get these zeros. And in fact, these, who has that here? Yeah. This is the underlying data. So here you see the decision-making styles on the vertical axis. And here you see the different operating systems. And then you indeed see that for 3 of these, there are no data points in there. So in this case, it wasn't that I typed something wrong in the command, because that's usually the thing that went wrong. You tried to do it and it didn't work because you forgot a comma somewhere or something else that delivered a typo. But here it was actually okay that it didn't happen, because for these 3 groups we have no data. Okay, also for analysis of variance, a bit of assumption stuff. And for that we need to hand wave a little bit more. Because as you can imagine, the more of these categorical variables we have, the more groups we are going to create for which we need to test that our interval variable is normal. So we have, let's say, decision-making type 1 with operating system type 1. And then one with 2 and one with 3, giving me 15 groups. So for 15 groups, I now have to test normality. Even if the variable themselves are normal, it is completely likely that I'm not going to find that this is going to work in each and every one of these cells. So it's not so obvious what to do here. So typically, again, the easier thing to do in terms of assumption checking is just this. If you have many categorical variables as well, this is just multiple regression. Do our standard test set for the assumptions in multiple regression and make sure that that will work. Again, an example why knowing both the analysis of variance and the multiple regression commands is useful. The grayed out stuff might work as well, but is troublesome as soon as you have lots and lots of categories. Okay, that is almost all that we need to know about these analysis of variance kinds of things. I want to take a couple minutes to talk about what the exam will be like. Because there are a couple things that are different that you need to know. First is there won't be any multiple choice kind of questions. There might be a couple questions where the answer can be relatively short, but the answer cannot be A. That would be wrong. So, in principle, all the stuff that you're going to get are questions that mimic the wiki material. So, all these wikis that you see online, all those are in principle questions that you could get at the exam as well. That implies that at the exam you are supposed to use Stata and Word and nothing else. And the way to test this for me is I give you a program that you should install on your machine. What the program does is make a log file of what you do. That log file you create yourself at the end of the session. And that log file you deliver together with your answers. You get a Word file with the questions in it. You can type your answers in the Word file. You can go to Stata to try to figure out what the answer is. You have to go to Stata, otherwise you won't be able to find it. You type in the Word file what your answer is, giving me enough so that I know what you did without overdoing it. So don't make, let's say, a huge do file and then say, yeah, the answer is 24. Look there. Because I'm not going to do it. So just explain what it is that you did and show me what it is that you did in such a way that I can replicate it if necessary. And make sure that you do not complete your answer just by giving output. Because then you also have to show that you know where to look at the output and what the right answer actually is. Otherwise it's not going to work. It is convenient if you could test before the actual exam what the easiest way for you on your machine is to copy output from Stata to a Word file. For some reasons this is not the same on all machines. So making a screenshot, for instance, with Paint, that's okay as well. And that might be the easiest way to do it, because simply copy-pasting output from Stata to Word might get tables all scrambled up and a little bit on the machine. So that's one way to check. Yeah.
Can you also use snipping too?
Yeah, that's one way to create a screenshot. So.
If that shows up in the log, it's no problem.
No, I think I know quite quite a few of the standard tools around, and if I find something else, usually just stick around with it. So if it's a screenshot tool. You're allowed to use Stata and Stata's help, so you can go to the help files. The help files, in fact, are also on your machine as PDFs. So that's okay. What you cannot do is consult the slide or the book or anything else outside your machine. So you cannot Google for, okay, what is again regression in Stata. All that is not allowed. There is one nasty consequence for part of you. You have to run the exam on a Windows laptop or on Windows on a Mac using Boot Camp. So there is what's that called again? So virtual machines. That's not allowed. Because there I cannot control what you do. And as long as you are running Windows natively, so Windows on a machine that does Windows, or Windows with Boot Camp on a Mac, then virtually can't get out of the problem. Let's see. Any questions? Yeah.
Well, can you use your own boot files?
No. That's something else that's not allowed. So you could say, well, I make a giant do file from all the wikis and all the stuff that I just put it there already. Now you have to start from an empty do file. So you have to know that to get regression, you have to type REG, and you cannot have, let's say, a reminder file for that. Yeah.
Can you use an example boot file and some controls?
No.
Because most of you will, I think.
Yeah, but that was a big nuisance for me for the checking afterwards. So it's, and also, the thing to be able to do before you show up at the exam is, let's say, make these wikis in a decent pace. So if you have to check every single command, what is this again, what is that, then you're simply too slow. So you have to memorize a couple of these things. If you practice a little bit, then most of these you either know immediately or you see, that's not right, fair. That's fast enough. Yeah.
If you can do all the wikis, then you're safe faster.
If you can do all the wikis, you do, yeah. If you can do all the wikis and you do not pass the exams, you can blame it on me. Yeah.
The exam will be only around the wikis, so no open questions or
No? What?
no open questions.
No. So the, okay, one important remark. So the point is not that the exam is about the wikis. So it's not that, question 1 of the exam that is wiki 7. There are questions at the exam that are similar to the ones that you could get on the wiki. And also, to protect myself a little bit, there could be questions in there that cannot be found in any of the wikis, but are consistent with the slides and all the stuff that we've seen over here. So I don't think it is a good idea to, I make a long list of all the questions that he can ask, because that's not how it works. Yeah.
Is it a possibility if you can take one of the wiki questions and work it out as we are supposed to during the exam?
Yeah, well, we're doing that all the time. So all the wikis that we have, the exam questions, in fact, some of them are or have been.
Yeah, but if you would add in the same answers as on the wiki, that's what is desired from us.
I think in general, add more comments than you think it is. Way more often I get, let's say, output or just a little bit of output where I somehow have to figure out what happened. So adding a couple of, and usually this might work well as long as your answers are correct. As soon as something goes wrong, then there's nothing else I can do than just trying to get it wrong all the way. So add more things. Yeah.
Do you have an example?
Yes, I'll do it. Anything else? Yes.
The exam we don't make will be online for it. I thought you were going to do
Yeah, what I'll do is I'll put an exam online. You can look at that yourself if you are able to do it. And time permitting, and that is dependent also on, for instance, on Friday.